Hi. Welcome to our tutorial, where you will learn how to set the design parameters, perform cross-section checks, stability design, and serviceability checks, and how to interpret the design results in Consteel, including using the section module. So, let's begin. I will continue presenting the workflow on the simple haunched frame structure we created in the basic modeling tutorial. Load cases and load groups are already defined, based on the loads tutorial video. In the previous video, we also saw how to perform the analysis on the frame. To begin, it's recommended to look at the Standards menu, where you can review the parameters of existing standards and easily create new ones if needed. Next, open the Global Checks tab. Both the Ultimate Limit State and the Serviceability Limit State checks are available here, although their settings appear in different panels. I'll start by configuring the Ultimate Limit State checks. The cross-section check, based on Section 6.2 and global buckling checks, based on Section 6.3.4, General Method, of Eurocode 1993 Part 1-1, can be fully automatically evaluated, as they are independent of any specific member parameters. As a basic setting, you need to select the load combination to be checked. In this example, I will choose the highest available load combination. The green checkmark indicates that the selected combination has been analyzed and is ready for use. In the steel design section, the first option is the cross-section check, which can be performed according to Eurocode 1993 Part 1-1 Section 6.2, or Eurocode 1993 Part 1-2 Section 4.2 if the load combination includes fire effects. You can also choose whether to perform the check for the entire model or just a previously saved model portion. For now, let's select the whole model. The safety factor can be adjusted as needed. If required, gamma M1 can be used instead of gamma M0 by ticking the checkbox. In this case, I will leave it unchecked. Now, I will go ahead and perform the cross-section analysis. The dominant results are shown in the table below. In this case, the highest utilization is 75.9% in load combination 5. By clicking on the corresponding entry in the table, you can easily identify the location of the selected finite element within the member. If we right-click on the row, we can open the section module by selecting the Calculate Section option. This will open a new window that displays all the section properties and resistance checks. All load combinations from the model are automatically imported and can be viewed in the table below. The relevant one is selected by default, but you can choose others or add new combinations manually using the New Load Combination icon. The stresses in this section can be viewed in the Properties tab. Here, you can see the normal stresses caused by axial force, bending moment, and their combined effect shown as the resultant normal stress, sum of sigma. You can also review various types of shear stresses along with their resultants. For visualization, you can switch between a colored figure and a 3D diagram to better understand the stress distribution. Let's explore the standard resistance calculations. For the selected loading case, the module identifies the required checks, performs all standard calculations, and determines the dominant case. For steel cross-sections, the standard design procedures performed on the elastic plate segment model cover the main steel design methods in the Eurocode, including the entire Eurocode 1993 Part 1-1 and parts of Eurocode 1993 Part 1-5. These procedures include calculations for general elastic resistance, analysis of pure cases, plastic and conservative interaction resistances for specific section types, and web buckling checks. In our example, the plastic interaction resistance gives the dominant result. Let's take a look at the bending about the major axis plus axial force check for the hot-rolled eye section, where the utilization is 75.9%, the same value we saw earlier in the Global Checks tab. Here, you can also see the applied part of the Eurocode standard with the exact formulas used for the calculation. Additionally, we can directly compare the design plastic moment resistance with the applied design bending moment. Let's have a look at the other results coming from different methods. First, we check the conservative interaction resistance, where the utilization is 80.5%. Next, the general elastic resistance shows an even higher utilization of 89.8%. So, why does Consteel select the plastic interaction resistance, at 75.9%, as the dominant result, even though the others show higher values? That's because the section meets the requirements for plastic design, and according to Eurocode 3, the plastic method is the most accurate and applicable in this case. The other methods are more conservative and are used only when plastic design isn't valid. But even then, you can still view all these results. They're calculated and displayed so you can compare and understand how the section performs under each design method. Let's close the section module and return to our 2D frame. First, I'd like to go back to the Analysis tab and calculate the buckling sensitivity, using all the static analysis settings we applied in the previous video. If you haven't seen that video yet, I recommend going back and watching it. With the help of this function, we get a summarized view of the buckling shapes of the structure, and for each member, it gives which buckling shape of which combination is the most relevant for the stability analysis. Based on this, the program can automatically select the appropriate critical load factor for each member that we can use in the buckling check. After the calculation is finished, we can return to the Global Check tab. In the ULS check panel, we can now turn on the buckling check, which is used for steel structures according to Eurocode 1993 Part 1-1, Section 6.3.4. Since we've already performed the sensitivity analysis for the elastic critical factor, we can enable the automatic checkbox here. Next, we need to select the ultimate resistance factor, which is the reciprocal of the utilization calculated using the characteristic resistances of axial force and strong axis bending. This is relevant when stability loss is the dominant failure mode. You can choose to evaluate this by members or by a model portion. I'll choose by members in this case. Finally, we need to select the reduction factor, which is an interpolated value between chi and chi-lt. The buckling check can be run either for the entire model or for a saved model portion, depending on your preference. Performing the calculation, the first thing that catches our attention is that the dominant examination method now is global stability resistance. And the maximum utilization is over 100%. Selecting the most critical result, I will open again the section module. The general method for lateral and lateral torsional buckling of structural components is used according to Eurocode 1993 Part 1-1. Here, we observe that the minimum amplification factor for the in-plane design loads to reach the elastic critical buckling load, with respect to lateral or lateral torsional buckling, is quite low, 2.23. Let's now examine the buckling shape in load combination 17. Notice how the bottom flange of the rafter, along with the haunch, undergoes buckling. To address this issue, navigate back to the Structural Members tab and insert 2-point supports to represent fly braces, thereby restraining the member in the critical position. Let's perform the analysis again with the same settings, and then rerun the design checks. Now, the dominant utilization remains governed by the global stability resistance, but it has decreased to 80.7%. As mentioned at the beginning of the tutorial, all standard-based verifications are collected in the Global Checks tab, including the serviceability limit state checks. By clicking the green arrow icon, a new dialog appears. Any previously defined serviceability checks can be found here if they were created, otherwise, it will be empty, as it is now. It is also possible to open or delete the selected checks from this dialog. To create a new serviceability check, click the New Check button. From all the available checks, we will select the horizontal displacement check first, followed by the global vertical displacement check as an example. Each serviceability check dialog box begins by selecting the load combinations to be examined. All relevant load combinations are automatically listed. You have the option to choose between calculations based on first order or the highest available order analysis results. Here, you can see a red X icon, which means that no second-order SLS combinations were calculated during the analysis step. Let's go back and fix this problem. We need to quickly return to the analysis settings and enable the second-order analysis option for the SLS combinations as well. Let's start a new check for horizontal displacement. Now you can see that the second-order results are also available. In the parameters box, we can set the displacement limits for both total and live loads. These limits are expressed as a fraction of the reference height or length used for the other checks, and the denominator can be modified as needed. We can choose to check the results for the entire model or for previously saved portions of the model. The check button allows for a quick calculation, enabling us to view key results. It is not mandatory to check the results immediately. You can save the settings and perform the calculation together with all other design checks. To save the settings of the serviceability check, it is essential to click the OK button. Let's also add global vertical displacement check. Here, we must set the first and the second structural point by clicking in the model to define the reference length. I will change the displacement limit for total loading to be over 150. And I will perform a quick check. And save it with the OK button. We can now close the window and perform the design. The first icon, with the two arrows, runs all the checks using the settings you've already applied. It's useful when you haven't made any changes to the analysis setup or load combinations, like when you've just updated a section and want to quickly recalculate. Let's take a final look at the results. You'll see 3 drop-down lists that help you review and interpret the output. In the first drop-down, you can switch between design results and pre-design parameters. Under design results, you're able to view not just the dominant results, but all the checks that were performed. These are organized into 2 main categories: ultimate limit state, ULS, and serviceability limit state, SLS. ULS results are further broken down based on materials and the type of calculation. Results from every load combination are saved, and can be accessed through the third drop-down. SLS results are grouped by the specific check criteria. For each criterion, you can see results for all load combinations, along with the dominant value. In our case, only the sensitivity data is available in the pre-design parameters section. That was our guide for the global checks in Consteel. Thanks for watching. Click the like button if you would like to watch more similar videos, and don't forget to subscribe.